Grid view. I don't know that I need grid view. I think I'm going to shrink your faces temporarily.
I just minimized it because
Yeah,
it gets in the way.
yeah. Not that I don't want to see your faces. Okay. So, so find the linearization L of x at x equals a. All right. So now we know the trick. When they say those words, linearization L of x, it just means find the tangent line. All right. So let's go for it. Well, we know that f prime of x, so with this first example, and again, I'm using this funky pen thing. You probably can't see it, but I have to like write on the trackpad off to the right. So I'm retraining myself with that. So we know the derivative of this function. I know you guys are all good at derivatives by now. So that's going to be 1/3 x to the negative 2/3. I know we got to get our mind moving again. So the derivative of this function is here. We know the slope of the tangent line is just the derivative evaluated at the point, which is a, they're giving us at a equals 8. So we want the slope of the tangent line at 8, long story short. So we're going to go ahead and plug and chug. Now you can, if you don't like mental math, you can literally type this out on your calculator. But it should come to be 1/12. So you type this out, it'll come to be 1/12. Okay. But once you get this, again, what is that? That's the slope of the tangent line. So note to self, slope of tangent line. And then again, how do we get the full-blown equation of the tangent line? Well, luckily, we've been doing that since the gate. So now we know to get the equation of the tangent line, we just bust out point slope form. And they gave us 8. So if I scooch that back up, okay, they wanted to know the linearization, which we now know means the tangent line, at 8. So 8's getting plugged in here. But you might say, okay, but what's getting plugged in for y1? Well, you got to put 8 into your original function. So it's like 8 comma something. Well, if I put 8 into the original function, cube root of 8 is 2. So that's like the location of interest. So then we know we're going to have y minus 2 equals 1/12 x minus 8. From there, you're pretty much back to basic algebra. So you'll have 1/12 x minus 8/12. And 8/12 is, what's that going to be? Well, you don't even have to reduce it because you have a calculator. Because at the end, you're going to add 2 to both sides, try to get y by itself. And then you've got 1/12 x, and then whatever negative 8/12. I'm using my handheld calculator because I don't feel like thinking. It's too early. Negative 8/12 plus 2, 1.3333. So 1 1/3 or 4/3. Okay, so after all that sweat equity, I'm going to page back up. Bing! After all that sweat equity, aha! That was the answer. Okay, so now, long story short, when you go to do the homework, you see problems like this, section 4.5, and they say find the linearization. Now it's nothing fancy. It's find the equation of the tangent line at that point. But for the visual people of the world, I want to see, like when we said, why would somebody want to do that? That's the big picture. Why would someone want to create the equation of a tangent line to a curve, or mimic the behavior of a curve near with a line near a certain point? So the best way I can explain that, what I'm going to do is do what we did from the beginning. Let's go ahead and graph the original. You can play with me or you could just watch. Graph the original, which, let me clear that out, which is, I'm going to type it in as x up caret 1/3. So I graph the original function. And then the idea is that if I shoot the tangent line at 8, this is kind of neat. And we know how to do that already with the draw tangent feature. At x equals 8. See, the idea is that if I were to zoom in near that location, not exactly at that location, but near that location. So let's say, okay, it's 7.9. So I'm going to hit trace. I'm going to go 7.9. Okay. And then I'm going to hit zoom in and hit enter. So there goes the actual curve. And now I'm going to hit, and then I'm going to hit, once again, I'm going to hit draw tangent. Let's see if my window is, will let me. Yeah, it will let me. So I'm going to redo the draw tangent, second draw tangent at 8. Look at that. That's what I mean by they're virtually indistinguishable. So the tangent line and the curve itself are virtually indistinguishable.
I'm not sure. Are you supposed to be showing a calculator or something?
Yeah. Oh, yeah. Can you see my calculator or no?
Sorry, no. We haven't been looking at your calculator.
Uh-oh.
No.
Oh, you can't see it. Isn't that bizarre?
Yeah.
Uh-oh.
It's still showing your regular.
When
That
you
is weird.
selected screen share, did you like select your desktop or did you select a specific window?
Oh, duh. I selected the notebook. So you have to select one by one. Oh.
Yeah, if you can just select your desktop, it should show everything that's on your
Oh, thank
screen.
you. Oh, let me try that. Okay, I'm gonna hit stop share. Okay, let me try that. I'm gonna hit stop share. Now I'm gonna hit share screen. And you're saying I can do my entire desktop?
If that's an option, yeah, then it should show everything that you put on that screen.
Let's see, what are the options? I feel like they make me do it one by one.
That'd be really dumb if that's
Yeah.
not an option.
Yeah, wouldn't that be oh, wait. Select window. It says screen. Should I hit screen?
Yeah,
suppose so.
unfortunately, I feel like you might have to toggle from
You think I might
your
have
share.
to toggle?
Yeah, you might have to bounce back from one to another. I know a lot of them don't allow you to view the whole thing just because it's a little.
No, I do have the option to just share one screen. For me, it just says screen one.
How about this? Can you see
Yeah,
it?
there you go.
Yep.
That
Yeah,
works.
woohoo! Oh,
That works.
so you didn't see my whole demo. Okay, well, I put in the function, yada, 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 right? And I hit draw tangent. Here, what I'll do. I had put in, I'll rehash that again. So I'll do zoom 6, right? So there's the original function. Now you can see it now, right?
Yeah, you're good.
Okay, good. Awesome. Oh, you guys are coaching me through this so much. Okay. So yeah, so then I was like, all right, well, let's go near 8, not at 8, but near 8, right? So I say, okay, trace, just go to like 7.9, 7.9. Okay, there, and then zoom in near 8. Okay, zoom in, boom, boom. Okay, so now I'm like near, I have a window that has me near 8, right? So if I hit trace, I know that if I draw now what happens is if I draw the tangent line, that's what I'm saying, it'll be virtually indistinguishable from the curve itself. So let's try it. So second draw, tangent, at 8 itself. And you can see it in real time. Just look at that. You can see it darker, a little bit darker, but it's like a way of saying that a line and a curve, so long as you don't walk too far away. Now, how far away did I walk, from, even if I walk, let's hit trace, even if I walk out here to 8.7, it's still fairly virtually indistinguishable from the curve itself. But boy, if I walk on out to say 10 or 11, it's going to diverge. So a line and a curve, a line can be used to approximate a curve. So long as you don't walk too far away, they call that an epsilon neighborhood or an epsilon tolerance. So long as you don't walk too far away. How far is too far? Well, you're typically given some tolerance level, or you're held within some tolerance level. But my question, and this is kind of a philosophical question, and this is a deep thought, why would someone in their right mind want to use a line to approximate a curve. Does anybody have an idea why that might be?
Sometimes a curve is you're unable to create a curve, so you break that curve up into segments of straight lines.
I don't have your face on. Who was that? Who was
Sorry,
that
that
speaking?
was Kevin.
Oh, it was Kevin.
Yes.
Okay. Oh, okay. um, say that one more time, Kevin.
I'm saying so sometimes you're unable to create a curve,
Yes.
and because of that you have to break up that curve into segments of straight lines. So in order to figure out
Oh, that's interesting. Yeah.
like where that curve is in relation to like just a straight line, I guess
That's interesting. I wasn't thinking. Yeah, and let me see if I can get you to say this. We haven't started there yet, but we're going to start there soon. What did we do to get the line right? We used it. We used the derivative, right?
yeah.
So it's kind of like if we have a derivative, we have a slope of a tangent line, and we now know we can use differentials, derivatives or differentials, to give us a decent approximation to a curve at a certain point. Yeah, so the idea is there ever a time, deep thought, is there ever a time where you have a derivative and you want to get back to the original function? That's called anti-differentiation, which we're going to start very soon in about a week or so. So the big psychology is this: if you know a derivative, you can get back to the original function with a process called integration or anti-differentiation. But there are some derivatives that nobody know that nobody knows what the antiderivative is to it. But we now know that that's okay, because we can use the derivative to help us basically cook up the equation of the tangent line to the curve at a certain location and give us a decent approximation, so long as we don't walk too far away from a particular value. But yeah, absolutely. So the idea that there's going to be some curves that are ornate and hard to operate on, and operating on a line, the easiest way to say it is performing mathematics on a line or a linear equation is easier than performing mathematics on some of these crazy looking curves that we're going to see in the future. But yeah, so that's kind of, if you're a deep thinker, you might want to be like, why would someone want to approximate a curve with a straight line? But my game, of course, is for now is to expose you to the language of the author, the language of the book, and the language of the homework. So when you see this fancy wording, find the linear approximation at a certain point, you don't have, this is what the author says, but now you just witnessed, you don't have to use that fanciness. You can use what you've always done, which is find the equation of the tangent line. It's just rebranded. So hopefully that'll help a little bit with that part of the 4 or 5 homework. You see that I just did what we've always done and did the equation of the tangent line to the curve at that point. Again, reminding you that all of these notes, not the audio, but the notes themselves, I'll post on my MATLAB. Let's see what's up to bat next here on the next slide. It says, let's take a look at differentials. Okay. Now, differentials are definitely a little bit tricky to explain. Well, okay. Difference in English, I always think of the English. Difference means subtract, means delta, right? If you say delta y, it means change in y. It means y2 minus y1. So I'm just going to read this for starters. It says, let f be differentiable on an interval containing x. A small change in x is denoted dx, and the corresponding change in f is approximated by the differential dy equals f prime dx. So that could be a lot to digest, but I'm going to circle the important part. Delta y, which also means dy, is the derivative of the particular function times dx. So if you think about it, I'm just going to say it like this. Let's say we're able to find the derivative of some function. Let's say we find that dy dx is equal to, I'm going to make up a Greek letter here. It's a lambda. It's not a made up Greek letter, it's a lambda. So let's say dy dx equals lambda. Then all that's saying is that dy can be found by then taking lambda times dx. All that is kind of like you're multiplying both sides of the equation by dx. And saying dy can be found by taking lambda times dx. Now, when you first read that, it's like, okay, well, what does that mean? So we pretty much have to dive with this. You pretty much have to dive right into an example and see what happens. So I'm going to start. I've snipped in a worksheet here. Well, it was part of the one from before. Start number 4 together. So it says, I'm going to start with this one. It says, express the relationship between a small change in x. So differentials is all about how does y change given a small change in x. So express the relationship between a small change in x and corresponding change in y in this form. So they're blatantly telling us what to do there, luckily. So they're telling us that dy, which means change in y is the derivative times change in x. Okay, so let's go for it here for number 4. I'm going to rewrite, I'll just rewrite it down here. So for 4, we're given that f of x is 5x squared, so I can write it bigger, minus 8x minus 9. We know the derivative, but instead of saying f prime of x, I'm going to say dy dx. We know the derivative is 10x minus 8. Now, all this is saying is if I want not dy dx, but just plain old dy, dy is just 10x minus 8 times dx. So again, it's kind of like you're multiplying both sides of the equation by dx to get dy by itself. And the way that translates to is delta y, or change in y, is the derivative times delta x. Now if I go and look at that answer, now that's matching up. It's matching up with the answer key. Okay. Now you might say, well, how is that helpful or how is that useful? And it's actually really cool how they used to do, and I'm talking hundreds of years ago, how they used to do, and Gauss, I'm talking Gauss here, a couple hundred years ago. It's like, we're actually going to dive into this one. It's like, how did they deal with cube roots, right? Of numbers that were not perfect cubes. So this is kind of fascinating to me, just as a number person. They clearly did not have a TI-83, and they could not punch in, let's go ahead and do it. Clearly, 34 is not a perfect cube, right? But we have this lovely little button, which they did not. And I'm not talking 200 years ago. I mean, even you ask your grandparents, they didn't have a TI-83. So, so cube root of 34. Now, see, I used a calculator, and I'm like, oh yeah, cube root of 34, 3.23. But notice here, the answer is 3.25 because it says use linear approximation and differentials. I don't know why the author didn't say that, because you're really using differentials. I'm going to say that here. It is linear approximation, but it's also differentials. To estimate the quantity to 4 decimals. So a long time ago, since they didn't have a calculator, they would use differentials to try to get close to the approximation for that cube root. So let's kind of see how that works for number 3. It's kind of interesting. I'll rewrite it down here. So we're interested in the cube root of 34, right? And that's not a perfect cube. So I'm going to call that y. All right. My question is, what is a perfect cube? What is a perfect cube that is, near 34? Well, 27, right? So I'm going to call that y naught. So y naught, let's call y naught, or like an initial guess, let's call y naught cube root of 27. So I'm picking a perfect cube that's fairly near 34. Because we know the cube root of 27 is 3, right? So I'm going to hold that thought. Just going to circle that. All right. Now I'm also going to go to the function here. So let's say the parent function. Let's just think of like plain functions. Let's say the parent function, I'll use f of x, so I'm not using y over and over again. I'll use f of x notation. The parent function, if we just think of it as a function, the parent function is the cube root function. So if I say that f of x is the cube root of x, question is, what's its derivative? Well, its derivative is 1/3 x to the negative 2/3. Now this is kind of neat. What happens if I take that, okay, and let me put here my PC, my perfect cube. I'm going to mental map this out here. If I take my perfect cube, I'm going to call it my seed or my guess. And let's say I call that my x, right? Or my x naught even. 27. So that 27 that I picked as my seed or my guess, my perfect cube that was near the original number, what happens if I take that 27 and put it right there? Well, we can crunch that out together. So 27 up caret, negative 2/3 is something. And then times by 1/3 is something. And then I'm just going to hit math frac as 1/27. Okay, so, or I could even keep the decimal part of it. Okay, so let me write that all out. So now, instead of f prime of x, I'm also going to switch to that notation, dy dx. So dy dx is 1/3 x to the negative 2/3. But we just witnessed that the derivative evaluated at that seed or that perfect cube of 27. And actually, I think I might rather like the decimal on that. Oops, did I remember to take it? Yeah, I did, 0.037. So that came to be 0.037. Okay, so now, according to what we just witnessed with the last problem, dy dx is equal to this, but g, if I'm only interested in dy or the differential of y, just delta y, and that means that dy alone should be equal to 1/3 x to the negative 2/3 dx. So now my question is, if we use that initial seed or that initial guess of a perfect cube, which was 27, because back then they had to pick the nearest perfect cube to the number that they were interested in. So 1/3 27 to the negative 2/3. My question is, dx means delta x, means difference in x. So I'm going to write this in words. How far away is 27 from the number that they originally gave us, which was 34? 7 units away, right? Aha. So dx just means difference in x. Just means 34 minus 27, that's 7 units away. So I'm going to plug a 7 in here. Now watch what happens. Watch what happens when we type all of that out. Well, we had already typed, the first part out. So I'm just going to go ahead then and times that by 7. 0.25, there we go. 0.2593 approximately. So dy, I'm going to record that. 0.2593. Aha, are you noticing something? Now, if I go back to the original problem, notice the answer, 0.2593. 3 plus that delta. Okay, so let me say that in words. So we use differentials. Dy is a differential. We use delta y differential to give us this value. And then what did we do to this value? Well, we added it to, remember from the beginning, I said that y naught, I'm going to pick a number close to this. We said that y naught was 3. Notice if I take y naught plus delta y, or another way of saying that is y naught plus dy, I get a good I get a good approximation. The easiest way I can say that is I'll get a good approximation for that cube root. So again, if you're a recipe kind of person, all I did was I took the derivative of the function. It's like I swung the dx up. I figured out how far away my perfect cube was, my initial guess, my perfect cube of 27. I figured out how far away that was from the number 34, which was 7 units. I typed all that out. I got 0.2593. What is that? That's my dy. But what do you do with your dy? You add it to the 3. So you can kind of, I mean, just by pattern recognition, you could see, okay, so if I take the dy, I'm going to highlight it way up here. And if I add that, my phone is distracting me. If you're like me and your phone's blowing up, I'm going to put that away. All my colleagues are like, they're all texting back and forth. We're on a math group text. They're all like reporting, how did your class go? How did your class go? So I don't want to hear them right about now. I'll talk to them later. It's definitely hard to teach this way, but it's better than not teaching at all, I suppose. I do see the chat box flashing, so I'm going to monitor that a little bit. Let's see here if it'll let me. It went away. Manage participants. It did flash me there for a while. Oh, chat. I don't see it. Oh, there it goes. It's going, predicting value. Okay, yeah. Oh, that was early. That was an earlier conversation. Okay. Yep. So a lot of people, long story short, if you're a person that like, how do you get the right answer? Like that's your goal in life is how do you get the right answer? When it says use linear approximation to estimate the quantity to 4 decimals, if I were to cook this up as a test question, I mean, it is linear approximation, but I actually wish the author would not have used those words. Wish they would have said use differentials. The thing that we really used there to do that was differentials, meaning that we took the original function, we found its derivative. We said that dy would be equal to this expression right here. And then what we did was we took a perfect cube, plugged it in for x, figured out how far away that perfect cube is away from the value of interest. Well, G27 is 7 units away from 34. So we plugged that in and we crunched all that out to get what's called your y differential. When you get your y differential, you tack that on to your y naught or your initial guess. So you say, well, the cube root of 27, I know that's 3. So if I tack that on, I'll get 3 point something. And gee, that 3 point something will be awfully close to the true. So long story short, they could get, and I had some of you might know her, she's in the Learning Center. Her name's Janaea. Any of you guys that are, and I know like Gabby, you're into programming. She's like, when she caught wind of this, she was like, oh, I'm going to create a program, that can get closer and like an iterative program that can get closer. Because if you think about it, think about how close I got to 34 by picking a seed to the cube root of 34, by picking a seed, an initial guess of 27, by picking a seed that was 7 units away. What if you could pick a seed that was even closer? You could get, but you have to pick, if you're doing it by hand the way I am without any kind of computer, you have to pick a perfect cube. So long story short, I hope that helps. So we can always backtrack. I want to get through all the notes. So we can always backtrack to some of these problems if you need to see them done. That's what they're talking about when they say use differentials or linear approximation to get this cube root. So they're not actually talking about get the cube. So if I pull up the cube root back when we did that, Notice the true cube root. Let's see how far off it is. The true cube root of 34, 3.24. And with our differentials, we're getting 3.26 approximately. So you're only like 100th off. So that's really not bad. So you're getting a decent approximation by doing that. Okay, now a little bit deeper here. Let's see what I have on the next slide. I think like if you can handle the 4, you'll be able to handle 5. I did 3. I might, 2's a little tricky. I might head back to 2. I'm going to be giving you guys a worksheet with answers. If you're really stuck, this worksheet with answers. So if you're really stuck, you can let me know. I'm going to temporarily dodge 2. I want to see what I have on the next slide. Yeah, because I wanted to take some time to revisit the problems that you had with the sub. And I really love number 5. So if you recall, this was what you did with the sub. And y'all did a great job on number 4, but a lot of you wrote, will you please do number 5 with us with L'Hopital's rule. So it's been a while since we've been together again. So L'Hopital's rule in your book, I believe, is 4.7, I believe. I have to double check the text numbers, but I believe it's 4.7. For no problem. So one thing you know now with L'Hopital's rule is if you're attempting to find a limit and it's an indeterminate form, like infinite, like this one would be infinity over infinity. If you have an indeterminate form, it's a classic candidate for L'Hopital's rule. This one, y'all wrote on your paper that you knew it was infinity minus infinity. That's an indeterminate form. That's basically your trigger. Either this or this, any of those indeterminate forms is your trigger to use L'Hopital's rule. Granted, this one blatantly says to use it. So let's see how that works. So the trick to L'Hopital's rule, though, is that you need a quotient. Big note to self. You need a quotient, meaning a fraction, before you operate. Meaning what? Well, this here guy's a quotient, right? It's rational. But this is not a quotient, so I have to force it to be a quotient in a legal way. So I love the algebra of number 5, so I'm going to do that one with you. So the limit as x approaches infinity, y'all are experts at the conjugate now, so the trick to this one lies within the conjugate. So I can magically multiply this quantity by root x squared plus 5x plus x, as long as whatever I do to the top, I do to the bottom. So you can't just, this is kind of like over invisible 1. So you can bust out the conjugate, but whatever you do to the top, you got to do the bottom. So that's the trick there. So when you do that, and then it's algebra from there, but there are some nuances in the algebra that I wanted to go over. Move my, my little text box there. So you're foiling with your radicals. So the radical times the radical makes the radical go away. So you have x squared plus 5x. And then outers and inners are going to cancel. So then it's just going to be x times x, which is x squared. So the top's going to clean up nicely. The x squareds are going to cancel. But what happens in the bottom is what's intricate. You still have this here radical in the bottom. So you're not quite ready to employ L'Hopital's rule. You're almost ready, but not quite. And you might not even have to. The problem with this one is if I were to straight up use L'Hopital's rule at this moment, if I put infinity here and infinity here and here, at this moment, I will currently have infinity over infinity, which is a candidate for L'Hopital's rule, but the problem is this derivative on the bottom is going to get real nasty. So what I would actually encourage you to do is an algebraic manipulation, and then you might not actually even need L'Hopital's rule. So I'm going to do something, and you tell me what I did. That's the safest way to do it. I think you'll catch it. I'm going to take this here 5x, and I'm going to times it by 1 over x. Oh, gee, but whatever I do to the top, I got to do to the bottom. So I'm going to times the entire bottom by that too. That's what they call an algebraic maneuver. And you only learn those maneuvers. I remember I used to see my professors doing that, and I'd be like, how am I supposed to know that? And that's the answer, just like coming to class and seeing people maneuver, or Khan Academy. Um, it's just little maneuvers, little tricks to help you get something cleaned up. It's legal so long as whatever you do to the top, you do to the bottom. So the top's going to clean up nicely. The X's are going to cancel. Top's going to clean up 5. And then guess what? This one's kind of misleading because it cleans up so nicely that you actually don't need L rule. You don't need L'Hopital's rule. Turns out you don't even need L rule if you clean it up using the algebra. If you use L'Hopital's rule, it gets pretty messy. So I probably should have been more specific on that. Actually, I think I meant, oh yeah, on that worksheet, there was like a subset of problems that said you do not need L'Hopital's rule for these. This one, actually, you don't, that was mean. I should have put it in the other segment. You don't need L'Hopital's rule for this one. You just need to clean it up algebraically like I'm doing. So we're doing that now. You could obviously use your calculator too to graphically find the limit. But down here, I thought it's a neat sort of gizmo that happens. If you send the 1 over x through via distribution, you're going to have 1 over x times root, x squared plus 5x. You just record that. Plus x over x. But gee, x over x is 1. So that works out nicely. So I'm going to keep cleaning. And I'm being lazy here with the limits. I would technically keep writing the limit as x approaches infinity the whole way down, just because my pen's a little crazy. So I'm being lazy with the limits. But I'm keep cleaning up algebraically. So now I've got 5 over something plus 1. But even at this, and this is the slick move that happens right here. Right when I get to here, I'm almost there. When you have a 1 over x outside your radical, you may bring it back inside your radical, but as over x squared. So I'm just going to go for it, see if you catch it. If you bring it back inside the radical, he's really, 1 over x squared. So I can bring him back inside the radical, but if I bring him back inside the radical, he's really 1 over x squared. That's legal. And then, isn't that pretty? Because then what happens? Well, gee, x squared and x squared cancel. And, 5 over x squared, reduces to 5 over x. And you have your plus 1. And now, after all that sweat equity, you do not need L'Hopital's rule. Because why? Because if you put infinity here, 5 over infinity goes to 0. And guess what? After all that sweat equity, 5 over root 1 plus 1, oh my gosh, it's so pretty algebraically, is 5 over 2. Root 1 is 1, final answer 5 over 2. So a lot of y'all had 5 over 2. Some of you used your calculator. Some of you maybe used Photomath. I don't know. A lot of you guys wrote notes to me. Even the sub wrote a note to me. That was my bad because I accidentally put it under the heading of use L'Hopital's rule. And that's actually a good moral to the story. There are, I'm going to box that out. 5 halves was that final answer. There are some problems where L'Hopital's rule could send you into some sort of spiral of purgatory. Like it doesn't work well on some problems, which is the tricky part. So I would say, because even me, when I first tried L'Hopital's rule on this, I'm like, oh my gosh, it's getting ugly fast. And that was my trigger. Like L'Hopital's rule is not supposed to make it get ugly. It's supposed to make it get easier. So if L'Hopital's rules make it get ugly, then that means that you do something else. You do an algebraic manipulation. So like this one is a candidate for L'Hopital's rule. Why? Because you just take the derivative of the top and you get 2x minus 4. And you take the derivative of the bottom, which is 3x squared minus 14x. And then you do it again. And I'm just going to write here ddx, I should say ddx. If I differentiate that again, that would send me to 2 over 6x minus 14. And then I could and then I could plug infinity. This one now I can plug infinity in for x. And 2 over infinity is going to go to 0. So this one, the limit as x approaches infinity, this one's going to go to 0. But long story short, that was my bad, because even the sub was like, hey, L'Hopital's rules get nasty on that one. I shouldn't have had it under the heading of L'Hopital. 5 was just algebraic manipulation, not L rule. So hope that helps. And like I said, I'll make these notes available. That is a classic manipulation of, I'm going to backtrack to that. How do you bring 1 over x back into the radical? You can, but you bring him in as 1 over x squared. So that's pretty classic. I see lots of chat box stuff. I want to make sure I got through the big money items, though. I know we're running close on time here. So we got L rule. Normally my lectures, like if I hold these like during normal class times, they're normally going to be shorter. We just had a lot of, it's been a while since we've been together. So let's see on the other slide. Yeah, this was actually something from your worksheet as well that I wanted to bring to the front burner. Rolle's theorem and mean value theorem. A little history. Michael Rolle, 1691, covered his original proof in 1691 covered only polynomials, and then Cauchy. We'll talk about the Cauchy sequence in Calc 2. Cauchy further proved it, extended it in 1823, but it always blows my mind that these guys were cooking this stuff up in the 16 and 1700s. Rolle's theorem, I'm going to kind of leave it here in the notes, but what I wanted to say in easy speak is Rolle's theorem in easy speak says that if you have a smooth continuous curve over the interval from A to B, there must exist an f of A and f of B have the same output. So f of A is here, f of B is here. They have the same output, the same height, if you will. And there must exist a turning point. That's all Rolle's theorem is saying. There must exist at least one turning point at point C. Now, at least one. There could be multiple. Visually, a turning point, we now know, is where the equation of the tangent line is 0. So I was surprised you all seem to have survived that one on the worksheet with the sub. I think I snipped it in. Let's see. Yeah, actually snipped it in. I'm going to fast forward here. It says revisit the worksheet from before spring break. Find the values of C that satisfy this condition in the mean value theorem. I thought there was one also for Rolle's theorem, but maybe I didn't snip that in. Let me see. Maybe I did not. I could probably retrieve it from somewhere. Let's see. Okay, well, I'm going to table Rolle's theorem temporarily because I didn't snip it in. I'm going to jump to mean value theorem. So what happened was I noticed like you all got it right. So I figured you digested it, but I wanted you to have Rolle's theorem just written out in all its glory. And it's only true. The big thing about Rolle's theorem is that it's only true that there exists a turning point between A and B if all 3 conditions of the theorem are met. So what are the 3 conditions? That you have to have a smooth continuous function on an interval, closed interval from A to B, and your function has to be differentiable. So smooth continuous function, closed interval A to B, your function has to be differentiable on the open interval from A to B, and you have to have that condition where f of A and f of B have the same output. So I didn't know what the sub gave you, so I just wanted mainly you to have Rolle's theorem in your notes. And then, like I said, I did notice some of you didn't have your work written down for this problem, so I snipped this back in. It was number 9. Find the value or values of C that satisfy this condition in the mean value theorem. You had it right, like your answers were right, but I just wanted to snip in the actual mean value theorem and what it means geometrically, and I'm just going to speak through that. It means geometrically this. When you say that f of b minus f of a over b minus a is equal to the derivative at some location. I like to look at a picture and think about it visually. Means that if you have a location here, and if you have a location here, so this location, we can call it a f of a. And this location here, we can call it b f of b. All the mean value theorem is saying is that there must exist a point C in between A and B such that the slope of the tangent line is synonymous with the slope of the secant line. So geometrically speaking, if you think about, when you do this calculation here, what calculation is that? Well, from the beginning of the semester, that was the calculation for the slope of the secant. Change in y over change in x. So then it makes sense what it's saying mathematically then. So then the slope of this blue line is the secant line, and the slope of this purple line is the tangent line. Their slopes must be the same because they're parallel. So when you say f prime of c, you're saying the derivative evaluated at c, well, that's the slope of the tangent line. So in words, f prime at c, that's the slope of the tangent line. So if you're, like I said, if you're a visual person, all this theorem is saying is that there must exist a location somewheres between A and B where the slope of the tangent line and the slope of the secant line are the same, that those lines are parallel. And you say, well, why must that be true? Well, it can only be true, again, so long as certain things are true. So long as that you have a continuous function, the function can't have breaks or gaps or holes over that interval. It's only true as long as you have a continuous function and as long as it's differentiable. So you're often looking at statements that are true if and only if your function is continuous and differentiable. So I know there was a lot to cover and I was going through that really fast and you probably fell asleep halfway through. But like I said, it's my job more or less just to broadcast the information. Now what I'm going to do is if you want to, and like I said, this was just a snapshot of the problem from your worksheet that you already did, and all of y'all had it right. I wasn't there to see how you got it right, but I'm going to open this up to a couple items. I wanted to share the syllabus with you. If you want to take yourself off mute, you can. Let me see here. I'm actually going to put your pictures back up so I can see your lovely faces. I'm going to share the syllabus. I did put this on D2L. Things for the good of the order. If you look at the layout, this lovely coronavirus is not going to stop us. Oh, I hear somebody, or maybe not.
Oh,
So, or if you have, I was going to say, if you have small kids or siblings, then maybe put yourself on mute. So it's not going to affect us much. Like it affects a lot of classes. But what happened was, I don't know if you got my note or my email. The math department has obviously taken away the need for face-to-face exams. The probability that we are face-to-face again before finals is slim. It's looking more and more like that every day. So I'm just kind of reading through the syllabus. If you did not get the email, is on D2L. This is our new syllabus, just so you know what we're doing every day. So first Zoom session, we did it. I'll put those notes. And I'll probably, clean it up a little bit and put some things in there. I'll put them on the document sharing in my math lab. But your game, I'm always trying to put myself in your shoes. And your game, I want to change to something here. Oh, let me see if I can I want to fix something here. Okay. Yeah. So your game from here on out will be, just finish your My Math Lab homework. Just try to come to Zoom sessions if you can. I realize life is crazy right now. So, if you can't, it's best to see it live if you can. You obviously have each other. You can set up Zoom sessions with each other. All my emails that went out to you guys, like if you hit reply all, it'll send it to everybody in our D2L shell. And you can kind of be like, when's the best availability for you? Typically it's Fridays or weekends, but now people aren't even working. So, Exam 3, you'll see. So I'm trying to see what we have built in here. 4.6 and 4.7. So if this is the big important part here. So next class we do we're going to do 4.8, which is L'Hopital's, or which is Newton's method. And exam 3, the good news is every exam from here on out, and I'm even gambling on the final, since all the exams are now going to be online and they're best out of 2 and they're not timed. My hope for all my classes is that the exam scores are skyrocketing. They should be good. No, because why? Because you have math. You didn't hear this from me, but you have photo math, you have Mathway, you have each other, you have YouTube. You know what I mean? So theoretically, the exam scores should be skyrocketing in all my classes because they're best out of 2. And you have so many resources at your fingertips. Now, like if you just use Mathway or PhotoMath to do the exam, like it'll help you on some of the problems. I'm just being honest. It'll help you on some of the problems, but it won't help you on all of them, you know, especially the word problems. But definitely, like if you take it once and then what's cool is you can go into review mode and you can see what you got wrong and then like take it again. And it's literally going to be the same problems, just different numbers. So you'll be able to assess that pretty easily. A big thing I wanted to say is since our exams are on my math lab from here on out, I would say write your workout neatly in a notebook somewhere so that you have that evidence. So like if there's like, if you're like, oh, you know, I did this whole problem, but I was only off by 0.2 because of rounding, you can send me an email and like a picture of your work or whatever, and I'll adjust the score. So, because the computer obviously doesn't have the ability to give you partial credit. It does have some built-in capability, like if it's a 2-part question and you got part 1 right, it'll give you like some partial credit, but it's not really good with partial credit. So save your work. You'll see from here on out, because we no longer have face-to-face exams, I was using that time to get us back on pace. So long story short, if I scroll down the syllabus, I still have us ending at a decent amount of time, like where we should have ended. So we basically were not drastically affected by that. Some classes that didn't have face-to-face exams may have been more affected by that. I see a lot of you guys are still on mute. Let me see, manage participants. I mean, I can hit unmute all.
Good question.
Yeah, anything you want to ask for the
So when exam 3 becomes active,
yes,
how long do we? Oh,
yeah, that's good. I know what you're going to say. Yeah, the other benefit of that is that you're going to have a full week to do it. So you're not sitting in a constrained classroom with an hour to do something, right? You'll have a full week to do it. Open resource. So theoretically, the scores should be high. And you didn't you didn't hear this from me, but how am I supposed to know if you're working with your brother, sister, cousin, boyfriend, girlfriend?
Nice.
You know what I mean? So.
Never heard a professor say it's okay to cheat.
What'd you say? Your other professor said what?
I said I've never had a professor say it's okay to cheat. Basically.
No. I mean, I'm just being realistic. How do I know? How do I know if you're using photo math? I don't know. So, so the hope is I've already seen what you can do. No, let me just say it like this. I've had colleagues say, oh, since they're now take-home exams, you know, we're going to make them extra hard. No, life is hard enough. We're dealing with a lot of stuff. I'm not going to make the exams extra hard. Right?
Thank God.
Okay, thank you.
Yeah, like we're dealing with a lot of stuff right now. I'm not going to make that's insane. So they're just going to be. Oh, okay. I did want to say this. Actually, I'm going to turn my camera back on. Oops. Let me see. Can you see me now? Okay, there we go. So I did want to say this. Remember how in the past, like everybody clung or cling, whatever the English word is, everybody cleaved unto my worksheets, and everybody was all about the worksheets because the test was going to look a lot like the worksheets. Well, the test isn't going to look like the worksheets anymore. So where is the best place to practice? I don't know if you realize this because a lot of people are like, "Oh, are you still going to give us worksheets? That's not the game anymore. The game's more about my math lab. So if you go into my math lab, you know how on the left it's like homework and then tests? If you hit tests, there's sample tests. So you should actually do the sample test for that chapter because it's going to mimic or it's going to look a lot like the actual test that goes out. What I do is it's the author's test. What I do is I go in and I look at his test and I have the ability to modify it and take off problems that I don't like. But unfortunately, your game is not my worksheets anymore because my worksheets are geared towards people in a live studio audience, in a live class. So now if I'm trying to get ready, if I want to feel for what these, online tests look like, I want to do the sample tests in my math lab to see what they look like because that's going to be more like it. And, people that needed double time or triple time, well, guess what? They now have it. You actually have a week to do it and there's no timer on it. So, and somebody asked, if you can get in and out of it. Yeah, you can get in and out of it.
Oh, that's
Yeah. So just make sure you don't make sure you don't hit submit, just X out. You can get back into it.
For the 26th, then we have a review due at.
Uh-oh. Wait, I'm actually gonna hit. Yeah, sometimes the audio gets. There we go. Okay. So
on the 20.
There we go. I hit mute. Now you have to unmute yourself because the audio was getting wonky between people.
So for the 26th, we still have a review with you at 9, correct? Then
let me pull up so it says 26 review day. Exactly. So, okay, good. So my intention from here on out, and today was like a lot of stuff, so it took a long time. I feel like normally Zoom sessions, like I can get through, pretty easily. We're really recovering for the 2 weeks of lost time. So these first couple Zoom sessions might take a little longer, but absolutely. I'm going to review on the 26th everything that's really, really important Power Pack concepts for this upcoming exam. What I'll do is I'm just going to outline, like skeleton outline, like be good at this, be good at this, be good at Newton's method, be good at L'Hopital's rule, be good, so I'll just outline and then I'll probably like put a little example, like how do you feel about something like this, as we go through the outline. Absolutely. So I still plan on meeting normal class time from here on out, unless something unforeseen should happen. I can tell I have a little bit of a head cold right now, but nothing serious. So yeah, I'm going to try to the way I am, like I need an agenda. So that's why I put out that adjusted agenda. If I don't have an agenda, it's chaos. So I'm going to follow that agenda the best I can. If you miss like these notes that I just did, I'm going to clean them up a little bit and I'm going to post them on the doc sharing. There's no audio, but the notes will be there.
Thank you.
Yeah. And people have already found my podcasts in iTunes U and through my screencast library. So like it goes in order from the beginning of it goes by titles. It doesn't go, it'll say like mean value theorem or L'Hopital's rule, so it goes by topics. Yeah. Anything else for the good of the order? Oh, who said that? Robert? Oh, okay. So Jacob, it's good you said that. For me, I'm cool. I'm cool with that. Other professors, you got to let them know that you're recording it before. Yeah. Yeah, because like I just basically told you to cheat on it. No, I wasn't really telling. I'm not worried about that. Yeah, no. If you want to put it up, that's cool. For me, I'm cool. And in fact, I told my other class, I'm like, we all clearly have gadgets and gizmos. Like the iPad has that built-in screen recording feature, right? So someone could clearly be doing that. Just out of curiosity, yeah, I'm cool with you doing that. Just like if you have other professors though, like let them know. Yeah. But just out of curiosity, Jacob, what did you use? No. Yeah. like
You
kind of like
use OBS. Okay, gotcha.
I'm writing that down. Oh, hold on. Streamlabs OBS. So long story short, I used like the Zoom. Okay, when I use the built-in Zoom feature that I have on my end, it says, sorry, not enough space on your computer to save this huge file or whatever. So then I tried Camtasia and that worked, but it took a really long time to cook it up as an MP4. And it literally took overnight. I let my computer cook and then cook it up as a YouTube file. So I was able to do it with my night class, but it took a really long time. And then I have to go back in and delete it and yada, yada, yada. So I'm actually kind of, how's the audio quality going to be? You feel like pretty good? All right. Yeah. I'm down with it. Yep. Yep. So where did you say you're going to put it? Oh, email me. You're going to email me the link. Oh, I see you guys. I see you guys playing with the annotating. Yeah, my students are playing with annotating. Feel free to play. The problem with annotating is like, yeah, unless you have a
I didn't realize it showed up for everybody. Oh wow.
Yeah, annotating. Yeah, it's nice. Like if I pull up a document, you can write on it.
I had no idea. I thought it was like just